Yeah, students, welcome back. Today we have to start the characterization of metal carbonyls. That when we get our synthesized metal carbonyls or carbonyl complexes, then how their structure could be deducted or deduced from the spectroscopic data. So we have to determine the bonding situation, bonding behavior of carbonyl ligand as well as the metal center. The phenomena what we have discussed, the back bonding and the forward bonding or sigma bonding and pi bonding. So in that case, from characterization tools, we will come to know that whether the metal participate in back bonding or metal is only sigma acceptor. And in the same way, we will also be able to say whether the carbonyl is pi acceptor or it accepts a pair of electron from the metal center, or the bond between metal and carbonyl is single, and so on and so forth, because we will also discuss some other types of metal carbonyls which are particularly important, and they are bridged carbonyls. So bridged carbonyls are those carbonyls where the same ligand, that is carbonyl, is attached to two or more than two similar or different metals at the same time. So they are called bridged carbonyl. So from this spectroscopic data, we will come to know whether the carbonyl is or the bonding between carbonyl and metal is single bond, or it is double bond, or it is triple bond. And on the basis of this bonding, we will also be able to predict the reactivity of metal carbonyls that we have already discussed, whether the carbon will be susceptible or exposed to nucleophilic attack, or it will be exposed to electrophilic attack. And same in the same way, we will also predict the reactivity of oxygen of carbonyl ligand. So the three characterization tools are very much important. Uh, they are FTIR, which is extensively used in characterization of metal carbonyls, and probably this is the only technique which has extensively used in characterization or structural determination of metal carbonyls. Then NMR, although the most reliable but less used as compared to FTIR, and we will also come to the reason that why NMR is less. This NMR technique is particularly limited to the system where unpaired electrons exist, or those metal centers where unpaired electrons are present. Then they are regarded as paramagnetic systems, and for paramagnetic systems, NMR technique is not applicable. So that is probably the only reason that NMR hasn't been used for extensively for characterization of metal carbonates. But no doubt the technique is quite reliable, and very useful information are obtained in case of NMR spectroscopy. And also this system is very simple, because it will give us only carbon 13 NMR signals, and carbon 13 NMR signals are very limited, or they are very less in a complex, based upon the number and types of bonding. In a complex, we have to get the number of carbon 13 NMR signals, while in FTIR there are a lot of signals, and particularly in assigning the IER spectra or the IER peaks, sometimes we face some problems, but here the problems are minimum. And third technique is X-ray. So X-ray is direct structural characterization technique, where direct evidence or direct structural features are given by this technique. So this is the most reliable technique, but the only drawback of this technique is that this data can be collected for a representative crystal. So this data cannot give us the information regarding the impurities present in our compound, while NMR and FTIR, they give enough information regarding the impurities present in the reaction mixture. In this case also the isomerism in the system or reaction mechanism cannot be studied with the help of X-ray crystallography, while NMR is quite useful in determining the isomers in the reaction mixture, even reactants, products, and intermediates. So, complete reaction path can be explained on the basis of NMR spectroscopy for a chemical reaction. The FTIR is also limited in this case because it does not give us, or it gives on the too much complicated spectra whenever products are more than one, or compounds we can say that more than one. So if reactant, intermediate, and product is present in the same sample, and we are determining FTIR spectrum of that sample, then we are unable to identify whether this is the starting material, this is the intermediate, or this is the product. So in terms of reaction mechanism, reaction path, this is the more reliable technique. In terms of identification of isomers or different products, NMR is again the simplest technique to give us an idea whether one isomer or one type of compound or more types of compounds are present in the reaction mixture. In terms of bonding, so FTIR also gives us some clues that what type of bondings are present in a molecule, but this technique gives very clear idea that how many types of carbon monoxide bonds are present in a particular reaction mixture. So let's start with IR spectroscopy. So FTIR actually gives a stretching phenomena and of a bond. So in this case, I will not go in more detail of IR spectroscopy because you know there are different stretching frequencies. They are vibrational frequencies of bonding. They can be scissoring, they can be rocking, or they can be only two and two motion, that is vibration. So vibration can be symmetric, asymmetric, and so on. But in this case, we are only concerned with the carbon and oxygen stretching frequency. This carbon and oxygen stretching frequency we have to determine in FTIR spectroscopy or IR spectroscopy in free state, and then after complexation with the metal center. So the bond between metal and carbon, it appears at lower frequency. Therefore, normally this range is either beyond the range of IR spectroscopy, or normally we do not measure this region because the IR spectroscopy, the normal range is from 400 to 4000 per centimeter, and this bond appears below 400 per centimeter. Therefore, normal people they ignore this region. Whenever we are interested, or we are going to know information or to collect information regarding this bond, then we have to measure the IR spectroscopy, particularly below the 400 per centimeter. So in this case, carbon and oxygen bond, it has certain stretching frequency, and for free carbon monoxide it is in the range of 2143 per centimeter. So this is free carbon monoxide, and it is clear that this is for gaseous carbon monoxide. So if this frequency decreases, so decrease means the bond order between carbon and oxygen decreases. And if this frequency increases, it means the bond between carbon and oxygen gets further stronger, and stronger mean the bond order relatively increases. So let the metal and carbon, they possess only single bond. So this single bond is observed only in the case of poor metals, and poor in terms of electron deficient metals. So those metals which are electron deficient, they do not have electron pairs in d orbital. In order to involve them in back bonding with this carbon, in order to give multiple bonding between carbon and oxygen, so such type of metals are called poor metals, and these poor metals are only capable to accept a pair of electrons from carbon in order to give single bond. So this single bond, so the normal range for This stretching frequency is from 1820 to